Okay, let's take a look at some examples of simplifying radicals. The first one is the square root of 300. And 300 is not a perfect square, so we want to determine if there are any perfect square factors. So we can do a little bit of work on the side. 300 is 100 times 3, and if we notice that 100 is a perfect square, which it is, we can now rewrite this as the square root of 100 times 3, or the square root of 100 times the square root of 3, and then simplify, so 10 square root of 3. Another option, if you were unable to see that 100 was a perfect square, or maybe you started factoring differently, you could factor completely and look for pairs of the same number. So in this case, we're going to look for, we have a pair of 5s and a pair of 2s. So what would go on the outside of the radical is 5 times 2. Because when you take the square root of 5 times 5, we get just 5. And when you take the square root of 2 times 2, you just get a 2. And so these are perfect squares that we have circled. But then it makes our simplifying a little bit easier, that we didn't have to actually pick out the largest perfect square factor. So 5 times 2 on the outside, and then square root of 3, the number or numbers that are left, and then just simplify. Okay, number 2, the square root of 12 plus the square root of 27. Okay, we can multiply, we can combine with multiplication, but we can't combine with addition between unless they have the same radicand. And in this case, they don't. So we will simplify each of these first. So square root of 12, okay, so 12 is 4 times 3, and 4 is a perfect square. So I would convert square root of 12 to 2, which is the square root of 4, and then times the square root of 3, plus. Well, 27 is 9 times 3, and 9 is a perfect square. Its square root is 3, so we get 3 square root of 3. And now we have the same radicand and the same index, and now we can just add these like we would x's. So 2x plus 3x is 5x. So 2 square root of 3 plus 3 square root of 3 is 5 square root of 3. And number 3, the square root of 49, x squared times 16y squared. We want to try to simplify this. So I notice that 49 is a perfect square, x squared is a perfect square, 16 is a perfect square, and y squared is a perfect square. Everything's a perfect square. And we're taking a square root, which is good. So we get the square root. So we get the square root of 49, which is 7. And then square root of x squared is x. Square root of 16 is 4. And square root of y squared is y. And then lastly, we can multiply these numerical coefficients together and get 28xy. Okay, number 4, we want to simplify the square root of 250 times x to the 5th y to the 6th. And we will kind of break this up. We will try to simplify the numerical part of the radicand. Okay, and so I'll just do a little bit of work on the side to do that. And 250 is 25 times 10, and 25 is the largest perfect square factor. So we end up with 5 square root of 10. okay, just by taking the square root of 25. Okay, the other things that we want to simplify, the square root of x to the 5th. Now, this seems a little tedious, but we could do this, the square root of x squared times another x squared times another x, because based on the power, one of our power properties of exponents, 2 plus 2 plus 1, that is the 5th power. But then I see that these are perfect squares, and so we take out, for every perfect square, we take out one of whatever the base is. So this is x times x will come on the outside, and then square root of x will remain. And altogether, that's x squared square root of x. Okay, well, again, that seems a little tedious, so instead, as a little shortcut, you could just divide whatever the exponent is by the index. So in this case, we're dividing 5 by 2, and we get 2 goes into 5 2 times with a remainder of 1. So that tells us this 2 should match whatever the exponent is. It tells us how many x's to take out, and the 1 should match how many x's remain. And in this case, there should be 1x. Okay, and then the last thing, we can apply the same rule to the square root of y to the 6th. And we can divide 6 by 2, and we're going to bring out 3 y's, or y to the 3rd. So altogether, we have 5x squared y to the 3rd on the outside of the radical, and then square root, we typically put the numerical part first, so 10, and then there was 1x remaining, so square root of 10x. And then number 5, we want to simplify the cube root of 32, x to the 3rd, y squared, z to the 10th. To do that, think about the index, which is a cube root. So we're looking for perfect cubes this time. So if I factor 32, I know that based on my perfect cubes 1, 8, 27, that a definitely goes into 32, so 8 times 4, and that is it. That's the largest perfect cube factor. So right away, we know that the cube root of 8 is 2, and then I'm going to leave a little space, and then we have the cube root of a 4 will remain under the radical. Now let's take a look at the variables. We have x cubed under a cube root, and so the cube and the cube root will cancel one another out, and we're left with an x. Y squared, in order to simplify the cube root of y squared, we need at least 3 y's, or y cubed, to be able to pull any factors out. And that is not the case in this problem, so we're going to leave y squared alone. But z to the 10th, there are some perfect cube factors, and how to figure out how many z's we're going to end up taking out, we can apply the same rule. Take the exponent 10, divide by whatever the index is, 3. 3 goes into 10 3 times with a remainder of 1. So that tells us we're going to have z to the 3rd on the outside, but there's also 1z remaining under the radical. So altogether we get 2xz to the 3rd times the cube root of 4y squared z.